All right, like I said, we're starting off in chapter 2, and this is the first section. It's the first of the 3 important topics in calculus, and the 3 major topics in calculus are going to be our limits, our derivatives, and then when we get into second semester, what's called integrals. So this is kind of the intro into our limits. The beginning part of this might look familiar to some of us because we were introduced to limits last year in pre-calculus as we talked about things like end behavior and such. And so first of all, one of the things we have to be careful of is that we are doing our notation correctly. Now, I know everyone in this room has seen this notation before, but some of us kind of got creative with our own writing and how we wanted to put this. So let me just point out some of the important things. First of all, the notation for limit is a normal size word. LIM is the abbreviation for that. And then the subscript underneath of it is where we say where x is approaching. And so we've got an X, an arrow, and then some number here, or an infinity is telling us where we're supposed to be approaching our X value. That is a subscript. It needs to be right underneath where you write LIM for limit. And then next to that, and this is where a lot of our pre-calculus, especially in like our regular pre-calcs leading into this, is that we can get a little lazy and like abbreviate this. But if you don't have anything following limit before you get to the equal sign, it actually doesn't mean anything. So you have to put something there. And you can put function notation, like referring to some function f of x that is written somewhere else on your piece of paper, or you can actually literally write the function there, like x squared plus 5, whatever it is, but there has to be something between limit and the equal sign. And that's telling us what function we're taking the limit of. And then equals, and then this would be our answer. That is some y value that our limit is approaching. So just a reminder on how this is read, I have it down here. The limit of f of x as x approaches c equals L. So giving some visuals. The biggest thing I can get out of this page is, guys, function value and the limit of a function are completely 2 different things. So the biggest thing I want you to know is that an open dot or a closed dot has 0 impact on the limit of a function. All of these are asking us, if you look at all 3 of these problems, it's the limit as our function approaches 1. In this picture, if you can tell, here's the origin right here. This is 1. And we are supposed to be approaching this x value. As we do our limits, we start on either side of that and trace our function towards that x value. And the question is, where is our function going? What y value is it approaching? Or if I were to maybe finish the problem, this is my x value, comma, where is my function headed, right? So if I trace on this side, I would be headed towards 1, 2. If I trace on this side, it's 1, 2. And whatever I would fill in here is the limit of that function. So we would say that this has a limit of 2. Notice there is actually no value there. Again, it has 0 impact on our actual limit. So I just want to show you that it could look 3 ways. No value there. This one has a value at x equals 1. Which is not 2, but the limit, again, as I approach x equals 1, is still up at 2. Even though there is a filled in dot somewhere else, does not impact our limit because that's not what we're approaching. That's what it actually is at that point, but that's not what we're approaching. And the last one, again, we've got now that filled in dot, again, does not impact my limit. We are approaching it, still approaching a value of 2. So what do I get out of this page? Open dot, closed dot, doesn't matter. At the value doesn't matter. What are we approaching as we get really close? Are there any questions on this whole visual of limits? Okay. When we are just handed a function to look at, not a picture, but they tell us actually what the function is, we have a couple different ways of figuring out what the limit would be. One of those, and the easiest and most direct route, would be what's called direct substitution. This is a great option, but is limited as long as what we are approaching, our a value, is in the domain of our function. A has to be part of the domain of our function. So when does that work? So here's some examples of when that would work. It works if our function doesn't have a domain restriction. So for example, any polynomial, it'll work for. So I could plug it in as long as, so I would just plug this in. I would find my limit by just plugging 3 in, direct substitution, sub it in, okay? I want to remind you back from pre-calc, those types of functions that you learned have domain restrictions, the ones we have to be careful of. Fractions, radicals in the bottom of a fraction, logarithms, all of those have domain restrictions. And as long as we are within the domain, it'll still work. For example, this is a fraction. Fractions, rational expressions, have domain restrictions. But this does not fall into that domain restriction, right? All I have to do on a fraction is check, can I plug this into the bottom and still get a number? Yeah, we have to be careful on a fraction that it's not a 0, right? But if I can plug this in and still get a number, no problem, still do direct substitution. Compare that to this next one, looks the same, right? This time, however, though, if I go to plug that -1 into my denominator, now I'm running into an issue. You are not allowed to do direct substitution when it gives me something like 0 in the bottom of my fraction. That will not give you a limit for that function. The other type, just remember some other types of functions that have domain restrictions, something like a square root. There are numbers that I could direct sub into that one. That particular example, I can't directly sub in 1 because 1 is not in the domain of that function. The function square root of x minus 3 has a domain of what? X has to be greater than or equal to 3, right? Because we can't take the square root of a negative. So I can't plug in 1, can't do direct substitution there. There are some problems that we can fix that with, so we'll look at that after we practice a couple direct substitution problems. Again, if it's just a polynomial, all I have to do is direct substitution. So the limit of this function, I don't have to look at a picture of it, nothing. I know what this one will be approaching as we head towards 2 by just plugging it in for x. So the limit is going to equal whatever this is when I plug in 2 for x. So I just go through the function, plug in 2, and let's see. 2 squared is 4 times 3 is 12, plus 4 minus 5. So the limit of that function as x approaches 2 is going to be 16 minus 5 is 9, 11? 11. That's a basic one of our direct substitution. Just looking at some other ones just to make sure that we are clear. Again, fraction doesn't automatically mean that we can't do direct substitution. Check the denominator. So I'm looking at this number right here and its impact on my denominator. If I plug -1 in there, we're still good, right? We're not getting a 0 in the denominator, so we can do our direct substitution. So the limit is going to end up being 3 minus -1 over -1 squared. I'll tell you guys right now, half the battle of calculus is remembering our algebra. That we have a double negative, that's a plus, right? And that when we square a negative number, we get a positive. And yeah, I know I sound crazy that I'm saying that here in our Calc AB class, but those are the mistakes we make. With that being said, on an AP exam, if this were to ever be what your answer was, you can always stop there. You never have to finish that problem. That's never going to be a free response question. They're going to be as multiple choice, so I'd have to go figure out what it is. But you don't ever have to simplify anything like this. You can plug it in and stop. So I would take advantage of that. Let's see, 4 over 1 or 4. Questions? Okay, the last one I just want to talk to you about as far as sometimes domain restrictions can hide in the formatting. So something like this, x minus 2 raised to the 1/3, I put this one on here so that we can remember. Sometimes we want to alter the formatting of our problem to be able to see things like domain restrictions or to be able to simplify out or whatever. I would rewrite this. Remember what 1/3 is? It can be rewritten as a cube root, right? Remember, fraction exponents and radicals can be rewritten as each other. And sometimes when I'm looking at a domain restriction, to me it's a little more obvious when it's written in the radical format. So this is the same thing as the cube root of x minus 2. And that stands out to me more as remembering that, do cube roots have domain restrictions? No, I can cube root anything. I can cube root a negative, I can cube root a positive. It doesn't matter. So it's easier for me to see here that I am fine to do my direct substitution. Cube root of -8 be -2. So those are all ones that we can do direct substitution. Let's look at a couple things that we can do when we can't initially do direct substitution. Some things you can try to clean up the problems and potentially still be allowed to direct substitute. We can't initially on this problem because if I were to put 2 into the denominator, we would get a 0. 2 squared is 4, minus 4 is 0. cannot do direct substitution, but the problem's not over. When we are looking at a rational expression, a fraction, we need to look to simplify if we can't direct substitute. So simplifying this one, take us back to Algebra 1 when we simplified rational expressions. Factor, look for things that cross off. Okay, so the bottom we are looking at there is a difference of two squares, x plus 2, x minus 2. Our x minus 2's are going to cross off. Please make sure you remember that the x plus 2 that's left is in your denominator. And then I reevaluate. It's not a guarantee that it's going to fix the issue, but a lot of times it will. I reevaluate, can I now do direct substitution on this problem? Yeah, now when I put the 2 in the denominator, it's not going to give me a 0. So I can put a 2 in here. 2 plus 2 is 4. The limit is going to be 1/4. At this point, I want to point one thing out. People are like, do I have to keep writing that limit over and over? Can I just do the work and then like put my answer? Yes and no. Just make sure that if you do not write the limit as x approaches 2 continually throughout there, you also can't use equal signs because they wouldn't actually be equal expressions. So if you're going to tell me that two things are equal, you have to have the correct notation. And again, that's going to be a huge thing as we head towards like an AP free response question. I don't get to say things are equal if they aren't actually equal to each other, even though I'm just being kind of lazy and doing shorthand. Got to be cautious on those types of things. Okay. Another one, this is just to help us brush off the rust on our algebra skills. Reminder, again, I can't do direct substitution because I can't put a 0 in the denominator here, but this one is simplifiable, right? There's a GCF up here. I don't get to just like cross off like this, yeah, right? Factor out your GCF and then simplify. So GCF in the numerator, x squared. That's when I can then cross off my x squareds, simplify out to something that I can do direct substitution for. Plug in that 0, and we get -5. Questions on that? Okay, and then also just a shake off the rust type of problem. Take a second and remind yourself how you factor that. Again, half the battle is remembering our algebra and making good choices with our algebra. You guys all have your own method of how you factor something with a leading coefficient other than 1. I guess and check. Again, looking for something that's going to simplify, and that simplifies out the domain restriction that we were having an issue with to do our direct substitution. So then I can do my direct substitution. Looks like we're going to get an answer of -5. Any questions on fixing rational expressions that are having direct substitution issues? Okay, some weird ones. These are kind of some standalone ones. When you run into a domain restriction that has a rational expression, but is not factorable to simplify, specifically has a radical in the numerator. Okay, on this one, we are going to use the numerator because that's where the radical is, and we're going to create its conjugate. Multiply top and bottom by its conjugate. If you've heard that word before, conjugate means the same two terms, different sign between them. So I would use that square root of x minus 1, the 2, and I would put a plus between them. I'm creating for myself a difference of two squares. When I multiply this together, I've created a difference of two squares there. Now I can't just multiply the top, or I've changed the problem. Remember, we're going to have to do that to the top and the bottom. Same two terms, different sign between them. As I do this, let's talk about what we're going to do in the top and what we're going to do in the bottom as going forward from here. In the numerator, you can FOIL that out if you want to, but it's a lot of work. It's a difference of two squares. When you multiply together a difference of two squares, if you think like a basic one, like x plus 5, x minus 5, remember that you always end up with the middle two terms dropping out and the first thing squared minus the second thing squared, right? X squared minus 25. It's the same thing. So it's the first thing squared minus the second thing squared. Well, square root of x minus 1 squared is x minus 1. So there's our first term squared minus our second term squared. 2 squared is 4. And then in the bottom, on a problem like this, we're never going to want to multiply that out because the entire purpose is that we are trying to get rid of this domain issue that we're having with the 5, right? So that's what I'm ultimately trying to cross off as we do this. Well, that's what crosses off, because if I were to clean up the numerator, that x minus 1 minus 4, minus 1 minus 4 is minus 5. X minus 5 is right here and right there. Common algebra mistake right here would be to lose the fact that this is sitting in your denominator. Remember, that is still in your denominator, so keep it in the bottom of your fraction. And now we can go to our direct substitution. 5 minus 1 is 4. Square root of 4 is 2 plus 2 is 4. 1/4. Any questions on that? All right. This one, some of you are more familiar with it than others, again, depending on what pre-calc you are coming from, and that is your greatest integer function. The greatest integer function is the closest integer to the number that you're plugging into, the intx, but is not bigger than the given value. So there's a couple ways we can think about this. That is the actual graph. If you were to type in this greatest integer function into your y1 in your calculator, that's the picture you're going to see. However, sometimes I think thinking about this on the number line is going to be our easiest way to think about this. If I were to look at a number line, okay, we're looking for, these are our only possible answers for the greatest integer function, integers. 0, 1, 2, 3, -1, -2, whatever. And they say, okay, look at this number. That's what I'm plugging into my greatest integer function, 2.1. 2.1 is going to be here. The biggest integer that is going to be close to that, but not bigger than that given value, well, the two integers that are close to it are 2 and 3. 3 is bigger than that, 2 is not. So the closest integer is always going to be the one directly to the left of wherever that would fall on the number line. All making sense? Yeah. Easy little trick when it is a positive number that has a decimal is it's just going to be the number in front of the decimal. So 2.1, its greatest integer is 2. Okay, well, if it's not a decimal, we might have to think what it is as a decimal. What would be our greatest integer for 1/2? 0, right? If I think of it as a decimal, it's maybe easier. 0.5, get rid of the decimal, it's 0.5. Or put 0.5 on our number line. It's always going to be that integer directly to the left of it. Okay? The negatives are where it gets a little tricky, messes with my head when I think negative. So I want you to talk to your table. Table come up with negative 4.3 is your number. What's the greatest integer function for negative 4.3? What are we coming up with? -5. And doesn't negatives kind of mess with you because you think positive numbers, what's not bigger than that? Well, -5 is not bigger than negative 4.3, is it? So again, sometimes I think thinking on the number line kind of helps with the negatives mostly because the negatives tend to mess with your head with greatest integer function. So little intro into greatest integer function. You'll see it pop up every now and then as we are doing some stuff here. The next two slides, guys, these are just memorization. You have to know these two limits. The limit as sine of x over x goes to 0, and the limit as sine of x over x goes to the infinities. As it goes to 0, first of all, if you were to have graphed it, this is what it looks like. As I head towards 0 from both directions, my graph is going towards 1. This right here is something you are just going to have to memorize. It's going to show up over and over. Also going to the infinities. So as we do the end behavior, out to the right and out to the left, Same thing. We're looking for this phrase right here, sine of x over x. As I head all the way to the right, or as I head all the way to the left, positive infinity, negative infinity, it's going to flatline at 0. If you think about why is that happening, sine of x has a range of -1 to 1. So this number will only ever go up to 1 or down to -1. As I head to bigger and bigger numbers, this is going to become a fraction like 1 over 100, 1 over 1,000, 1 over 1,000,000, which is why it's going to 0. Okay, so that's the kind of quick explanation of why these are what they are, but ones you're going to have to use. We are going to try to find this little fraction within functions to be able to help us break down and find limits of more complex functions. So let me give you one example. The limit as x approaches 0 of sine squared x over x. What I want to do when I'm given this, if I see something that kind of resembles this a little bit, I want to try to break it down to see if I can isolate it to say sine of x over x. So some things that I want you to look at, sometimes looking at these in a different format can help. For example, sine squared of x would be the exact same thing as sine of x squared, right? So those are the exact same thing. The only reason I do that is to remind you that if something is squared, that means it is that thing times itself, right? Or sine of x times sine of x. So I really could even rewrite it more as sine of x times sine of x. And if it's multiplication, I can really break it into the two fractions, sine of x over x times sine of x over 1, right? And that's what I was trying to get. I was trying to isolate that fraction to somewhere say sine of x. And then the other little thing I have to remember is my limit laws. And that is, in my limit laws, is I can take the sign of each of these, or I can take the limit of each of those individually and multiply the results. So I really can look at this as the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of the sine of x. Okay, well this one we now know. As sine of x over x approaches 0, we are going to head towards 1. Question? Right. So that's why we're going to memorize this. There is another step that we would have had to take in this one that we're not going to learn until second semester that will have explained how to take the long route of this limit. Yeah, so that's why I'm just handing it to you now. L'Hopital's rule, when we get to right before our AP exam, will explain to us why we can actually get a limit at this, even though I can't do direct substitution. Second one, limit as x approaches 0 of sine of x. This is where I've got to do a real quick reminder. Make sure we all remember what sine of x looks like. Remember what your sine of x graph. You guys remember doing all of this second semester last year, and it looked like this little guy right here. Yeah, looks familiar? Okay. Well, as we approach 0 from the right and from the left, that graph is headed towards 0. So the limit as we approach 0 would also be 0. Well, 1 times 0 is 0. Questions on that? All right. The last little bit, and I'm going to fly through this part of it. Okay. What if I try direct substitution? It doesn't work, which would happen here. Can't plug in -1. What if that is not a fraction that can simplify? Also true. What are my other options? One of those I would say is to look at the graph. See if looking at the graph fixes it. Sometimes it does, sometimes it doesn't. It might explain why it doesn't work on this one. This one actually does not exist. That is not in the domain. If you remember how to graph something like 1 over x plus 1, this would be moved to the left 1. Those types of graphs have vertical asymptotes. It would have looked something like this. Well, the two sides of my graph are not going to the same place, right? As I approach -1, my left-hand side is headed down towards -infinity, and my right-hand side is headed up towards positive infinity. The limit, since those two sides don't match, does not exist. So it is okay to have limits that do not exist. You can describe those any way you want. Do not exist, undefined, not defined would all work. Same thing would happen here. Again, I would think about the domain. -3 is not in the domain of this graph. The domain of this graph would be x has to be greater than or equal to 1. If I were to look at the picture of this, this is moved to the right 1. It looks something like this. -3 is over here. Well, it's not approaching -3, so it doesn't have a limit at -3. It's not in its domain. So again, does not exist. In AP, these are just two other examples of it not being in the domain and me not having an option to fix it. AP does not necessarily say undefined. They use does not exist, or sorry, uses undefined instead of does not exist. It doesn't really matter. I feel like if you came up with does not exist, you would be able to pick that out of a multiple choice where it said undefined, right? You know that those match up with each other. All right, the last part. This is the more calculus stuff that we haven't seen before. A couple of vocab words for you. Average rate of change is going to show up all year. Average rate of change or average speed. You guys have probably heard the phrase average rate of change before. Those are fancy math speak for the slope, and we know slope formula. I don't want you to get distracted by the math terminology and the math notation that's used on this. This is slope. That is y2 minus y1 over x2 minus x1. That's all it is. It is your slope formula, which you guys have known and used since middle school. Okay. So if they ask us for the average speed of something or the average rate of change, we are going to do the slope formula. They will give us the x values in an interval. And we then have to plug those into the function to find our y values and do slope. Okay. This one is built off of that, but it's what's called instantaneous. And this one would just be at a single moment. So if they ask us for the instantaneous speed or the instantaneous velocity, and it will ask you at a specific time, at time equals 4, at 3 seconds. You'll notice the difference between that and given an interval. So they give us 1 moment in time and we're supposed to find the tangent line. Well, a tangent line is just at a dot and the line that would go tangent to our graph. So how am I supposed to find its slope? It's still built off of your slope formula. So let me give you a little kind of breakdown of this. Basically, if I were to talk about this point right here being at, let's say, x, some x value, and then I pick a point really close to it. So that one would be at like x plus some number, where the distance between these would be h. Right? So I'm just a little bit farther away. Well, basically what I want to do is to get it to just be that dot instead of the 2 dots, is that I make h so small it's practically 0. That I'm so close, h is negligible. Okay, well, how do I do that? We use limits and we make h approach 0. But what you're going to see as I set this up is it's still just the slope. It's still the slope between those 2 points. So the 2 points would be this. The function at the second point, x plus h, minus the function at the first point, over my 2 x values, x plus h minus x. But I want h to practically become 0. And the way I do that is to, instead of just using the slope, is to make it the limit as h approaches 0. I want h to become negligible. The other thing that would get cleaned up on here is, first of all, look at the bottom here. X plus h minus x. Well, would there be an x there? No. So the formula you guys will see for instantaneous speed, instantaneous velocity is this. The limit as h approaches 0 of f of x plus h minus f of x over h. It's not a made-up formula, but that's cleaned up. It's slope, but x minus x is cleaned up out of the denominator. This is the one you want to know. Questions on that? Okay, so let's put those 2 formulas into action here, see the difference between them. First question is an average rate of change example. It says a rock breaks loose from the top of a tall cliff. What is its average speed? So average speed is telling me slope formula. During, and then sometimes we have to do a little bit of interpreting. During the first 2 seconds of fall. The first 2 seconds of fall is telling me that they want me to look at the interval from 0 to 2 seconds. When they word it like that, during the first 2 seconds of fall, 0 to 2 seconds. The next part gives me my function. Experiments showed that a dense object dropped from rest to fall freely near the surface of the Earth will fall at this rate, y equals 16 t squared feet in the first t seconds. So here is my f of x, or my function, that I'm going to be putting into our formula. So if you remember, average speed is just going to be your slope formula. So our slope formula says f of b, the second number, f of 2, minus f of 0 over 2 minus 0. Okay, well, we know what the function is. The function is actually 16t squared. So I'm going to figure out what f of 2 and f of 0 are and put them in that fraction right there. F of 2 would be, let's see, 2 squared is 4 times 16 is 64. 0 squared is 0 times 16 is 0. All right. And then we get to one of the next most important things when we are giving answers in AP, and that is our label. So how am I supposed to figure out my label? Go back to what we're looking at. F of x, f of t, is in feet, right? So f of t is feet. 2 and 0 came from up here, and those are seconds. So our answer would just be that fraction right there, feet per second. Now I want the instantaneous velocity at 3 seconds. Now notice again, no longer are we looking at an interval, we're looking at time equals 3. And so this is where we go to that limit and we make h go to 0. So let's look at what that looks like. It's got a little bit of work behind it. So we're going to look at that instantaneous velocity formula. The limit of our function is h goes to 0. So our function is going to be this. F of, and our t, or our x, is 3. H will always be h. So it's going to be 3 plus h minus f of 3 over h. I'm going to flip back to this page real quick here. The x's are where you get to actually put in values. The h's will stay h's as you do this. Okay, so when you're given that instantaneous velocity question and they tell you your time, that's the number you put in there. Okay, but we're actually going to plug those into the function. So our function, remember what our function is, or f of t I should say, is 16t squared. So where there is a t, I'm plugging this in. So we're looking at, let's see, 16, 3 plus h squared minus 16 times 3 squared over h. Are we all okay with my jump from here to here? Right? I just used the specific function instead of the notation f of x, right? Okay, now this takes a little bit of cleaning up. Remember that if I've got a binomial squared, I have to FOIL that, right? So it's going to get a little uglier before it gets prettier. Ultimately, I cannot do direct substitution right now, so that's why I'm going to clean this up and then do direct substitution when I finally am able to simplify that h out of the bottom of my fraction. Takes me just a couple steps here. So first of all, as I FOIL that, we're looking at 9 plus 6h plus h squared. 3 squared is 9. Distribute the 16 through now. Let's see, 16 times 9 is 144 plus, I think, 96h plus 16h squared. Good so far? All right, what you'll notice is I have 144 here minus 144 at the end. Aren't those just going to cancel for me? And the remainder is a 96h and a 16h squared. They have a GCF of h. And so what I can do is pull that GCF out front so that I can simplify it with what's in the bottom here. So pull that h out front, leaving me with 96 plus 16h. And that allows me to simplify out the issue I was having there in the bottom so that I can now do direct substitution. I can plug 0 into the 96 plus 16h, which gives me an answer of 96. And again, label. What is my label? Well, guys, we're looking at the same thing we were just looking at in the other problem. The top is your function, which your function is measured in feet. The bottom was your x's, which is measured in seconds. And so my answer would again be feet per second. Questions on that? Okay, we're going to have to probably pause there. Like I said, if you want to see my work for the last example, it is on that class Google Classroom that I showed you before, and your assignment is on page 66, and you guys all now have access to the online book. Don't delete my